Hey folks, picking up where we left off last time, we're going to continue looking at some more hard problems, and then we're going to connect them to each other today. Alright? So, last time we looked at Clique, and we also thought about traveling salesperson problem. Let's start today by looking at another seemingly simple problem, but one which has no known polynomial time solution, no efficient known way to solve it. This is the independent set problem. You'll see this abbreviated in my notes to just IS for independent set. The input is again an undirected graph, just a graph, vertices and edges, and also an integer k. Same sort of input you saw for Clique as well. And our output is just whether the graph contains an independent set where that independent set has a size greater than or equal to k. Alright, so you want to find this thing called an independent set of size k or greater. Now, of course, we need to know what an independent set is. So an independent set in a graph is just a set of vertices with no pair of them connected by edges. Okay? So if we look at this example down here, B, D, and I would be an independent set. There's no edge connecting any pair, B, D, or I. B, D, F wouldn't be an independent set. B and D aren't connected, B and F aren't connected, but D and F are connected. Right? So you want to find a bunch of vertices with no connection between them, and you want to put as many vertices into that set as you can. So looking at this example, why don't you stare at this for a moment and see what the largest set of vertices you can find with no connection for any pair is. Yeah, so try and find the largest independent set for this guy that you can. Alright? So hopefully you got a guess in mind. Let me look over it and see what we should do. So starting off with looking at G, H, and A. These guys are connected to each other, so we can only pick one vertex inside of this set of three. So why don't we take, I don't know, doesn't really matter. Let's say we take G. So if we take G, then we can't take A, we can't take H. Because they're connected. But we could still take B or C. Now these are connected to each other, so I can only take one. That doesn't really matter which one. Let's just take B. Then we can't take C. And then let's see, we could take E. That would be one solution. Once I take E, I can't take D, F, or I. And that would give me three vertices, which form an independent set. But we can actually do better by taking D and taking I, right? And then we don't take this guy, we don't take this guy. And we end up with four vertices that form an independent set. All right? These guys, G, B, I, and D, form an independent set. You could ask, hey, can I do better than that, right? Is there a better set to choose? Well, it seems like kind of not, right? We're sort of excluding every other vertex from this guy, but feel free to play with it and see what you can come up with. So this is independent set of size 4. All right. So, if that makes sense, yeah, if we're okay with that, then let's do another one here, just for some practice. Sorry that this graph's a little bit uglier. You'll see why it looks like this, why I drew such a weird looking graph in probably just a minute here. But before that, why don't you look and see if you can find an independent set for this one. What's the largest independent set you can find? Okay. So, looking at it, maybe there's other ones. I'd have to stare at it for a moment to verify, but the one that stands out to me here are these guys. C, B, D, and F. again, no direct connections between them. You're allowed to have indirect connections, like B to H to C, but there is no direct edge connecting any pair here. Okay? So that is an independent set, also of size 4. Unlike the previous graph, I think it's a little bit harder to see that this is optimal. You know, you could try vertices and see that none can be added, like A can't be added because it connects to D, E can't be added because it connects to D, H can't be added because it connects to B, G can't be added because it connects to C. So you can pretty quickly run through the vertices and see that you can't add any of the remaining ones. But you might be rightfully looking at this and being like, but is that the best? Is there an independent set of size 5 that we just aren't seeing? Now, to answer that question, or at least rephrase that question, does this problem that we're solving here with independent set remind you of anything? Now, this specific problem, or the idea of independent set in general, does it remind you of anything? So get your answer down. What this might remind you of is the Clique problem. You'll remember the Clique problem was trying to find a set of vertices who are all connected. Now we're finding a set of vertices who are all not connected. In a sense, what we're doing is kind of the mirror operation. We're doing the exact sort of opposite operation. And maybe you even realized that looking at that weird graph here, what this is the graph we had for Clique. See the same vertices in the same locations. But I've reversed all of the edges. Everywhere we had an edge before, I've put no edge. Everywhere we didn't have an edge, there's now an edge. For example, H previously was connected to nobody. This H is connected to literally everybody. To G, to A, to B, to C, to D, E. You have this long edge here. F, connected across for this edge. So this is kind of the opposite graph of the one we had before, and the vertices which form our independent set of size 4 are exactly those vertices which formed our clique of size 4 before. Right? That's maybe some justification you could use to realize that, yes, this is the independent set, the largest independent set, because it's the same logic as to why that was the largest clique in the previous graph. Interesting. Okay, so this is similar to clique problem, just with our edges kind of reversed. You know, the edges that existed before don't exist, and the ones that did exist, that didn't exist now do exist. Cool. All right. And that now allows us to draw a connection between these two problems. In particular, what I want to show on this next slide here is that if we someday found a way to solve independent set efficiently, like tomorrow you read in the newspaper or in the journal that, hey, an independent set solution was found that runs in polynomial time. Again, polynomial means n to the constant. If this guy existed, that should tell us that clique is also solvable in n to the constant time, in polynomial time. How do I know that? Well, this is, I know, probably harder to see on your screen depending on how you're viewing this. You can go grab the slides, but I have a little kind of figure here to demonstrate the idea. Suppose someone solves independent set. I could treat their code kind of like a black box, right? You know, suppose our clever friend solves independent set, claims to have solved independent set, but they don't want to show us how they did it. So they refuse to tell us what their code does, and they won't let us look at their actual source code. We could still solve Clique by using their solution as part of ours, as a subroutine in our solution. So they have a solution for polynomial time independent set to solve Clique in polynomial time. So it's this box, this black box represents our friend's code. This larger box containing it represents our Clique polynomial time solution. We could solve Clique using their solution as a subroutine by taking in our graph input and taking in our Clique size input, transforming that input in some way, and then using that as an input to their independent set solver. Then, whatever their independent set solver says is true about this will also be true about our original Clique problem. That makes sense? So we're transforming a Clique problem into an independent set problem. This is really the core idea of what we're going to be doing in the next slides on NP hardness. This idea is really core to what we're doing. So it's good to try and understand that, make sure it makes sense. I'm going to walk you through this first reduction. In fact, I've kind of already have with the previous slide. So suppose you have a Clique graph input. So you have a graph for Clique, G sub C, which consists of the vertices V sub C and the edges E sub C. And then the Clique K input will denote as K sub C. The independent set inputs, similarly, are also V, E, and K, but I'm going to put an IS to represent the independent set inputs. Now, to turn the Clique inputs into independent set inputs, equivalent independent set inputs, how do we change them? Well, we saw on the previous page the size, right? When we were looking for a clique of size 4, that became an independent set of size 4. So the size of the independent set we're looking for is the same. Yeah, basically no change. And the set of vertices we use will be the same as well, right? We didn't change any vertices. We didn't remove any vertices. What we actually did on the previous page to turn in a clique problem into an independent set problem, or vice versa, was we took the original edges that were given for our clique and we reversed them. So this is just the negation of the edges that exist, aka if you have an edge A to B, which is not present in the original set of edges, then it is going to be present in the new set of edges for independent set. There's a little bit of set builder notation. If you haven't seen that in a while, all this is really saying is anywhere we're going to have all edges where that edge was not present in the original set of edges. Okay? And that's the whole reduction. Right there, we've just taken an input to the clique problem, and we've turned it into an independent set problem, which will give the exact same answer. Right? And if you don't believe this, go create clique problems, use this to turn it into an independent set problem, and see that they have the exact same answer for that K you specify. All right? And moreover, how long does it take to do this? How long to, again, we'll call this reverse the edges, this operation. So it's like reversing the edges. You could think of it as the complement operation, if you're familiar with complement, but whatever. How long does it take to reverse all the edges? Well, we have to take every edge that was present before and remove it, and every edge that wasn't present before and add it. So it's basically the number of vertices. This is number of vertices in the clique. Well, we need to reverse every possible edge, and that's the number of possible edges. So this is O(n) time, because this is number of possible edges. It's an undirected graph, so it's technically this guy divided by 2, right? But that doesn't change the asymptotic runtime. Okay? So these operations up here take the number of vertices squared time. That's polynomial time. So we can turn a clique problem into an independent set problem in polynomial time. I can turn any clique problem into any independent set problem in polynomial time. This proves, this little notation we use here is for reduction. This proves that clique is reducible in polynomial time to independent set. So if you want to read that, you can read it as reducible in polynomial time to. Clique is reducible in polynomial time to independent set. And technically, we could also show the reverse. We could show that any independent set problem is reducible to clique. It's the same idea. So just to, I guess, use a little bit of notation here, you could think of this as being equivalent. These two problems are equivalent, give or take a polynomial time factor. Okay, and so hopefully you see now, if I find a polynomial time solution for either of them, if I find an efficient solution for either of them, I have found an efficient solution for both of them. All right, so that is the independent set problem. We see it's just equivalent to clique. If you have any doubts about that, again, try out the reduction, think about it. I do have another example, though, for you, if you want some more practice with this. All right. So, continuing. Continuing here. Let's try out another seemingly pretty simple graph problem. This one is the vertex cover problem, abbreviated to VC. And again, this is an undirected graph problem, and you're given an integer k greater than or equals 0. Okay, so same idea as the previous ones in terms of inputs. We ask, is there a subset S of the vertices such that the size of S is less than or equal k, such that every edge in the graph is incident to at least one vertex in S? Okay, so this is a bit of a mouthful. But the idea is we want a set of vertices which essentially touch every edge. A way to maybe think of it is if you had a graph, very simple one that looks like this, and you wanted to think of these as maybe roads, right? This is a road, this is a road, this is a road, and you wanted to have a guard that can view every road. So you want some guard to be able to, for every road, see down it. So you could put like a guard here. That guard can see down this road, see down this road, see down this road. But there's a road that they can't see. So we would need to add a second guard for this example. Right? And then that guard can see down these two roads. Now every road has a guard associated with it, someone who can see down that road. We want to figure out what's a set of k locations to station these guards so that every edge is visible. Okay, for this first one, I want you, as before, to think about this. See if you can figure out where would you place sort of guards to make sure that every edge is visible. Right, every edge is visible to at least one guard. All right. So one solution you might have come up with is to just start at A. You might have said, okay, I could put a guard here. Well, then this edge, and this edge are covered. So we don't need to worry about those ones. Let's see, where's an uncovered edge? Well, let's see, we have this edge, that's uncovered. So we could put a guard here to cover that edge. And they cover these ones in addition. And let's see, we could put a guard, say here. That would cover these three. And then we could put a guard here. That would cover these three. Right? So those highlighted vertices right now, putting one person on every single one of those, marking each of those as part of our vertex cover, that does cover every possible edge. There's no edge between C and D or C and B or B and D. So all of them are covered. Okay, so that would be one possible vertex cover. This would be vertex cover of size 4. Now, there's many different ways to get this. So we could also have picked, instead of E and G, we could have picked like C and B. Those would have also worked. So multiple ones that will work. Can you find one that's smaller? Well, actually, yes. It turns out, in this example, D, C, and B also forms a vertex cover. If you put your guards here, every edge goes between one of these outside edges and one of these one of these outside vertices and one of these inside vertices. There's no edge between an outside pair, and there's no edge between inside pairs. So the inside set also works. All right, does that make sense? So go through again and mark these. And cover everything. All right. All right. Now, not everyone has this kind of nice symmetry. Here, the vertex cover was two different kind of possibilities, two easy possibilities we saw that were just happened to be opposite sets of vertices. That isn't always the case. Let's try out this graph here. This is the one that we used for independent set. Where could you station your guards in order to cover all of these? I'll give you, again, a little bit of time to think about it. So, the guards, let me see, a good place would be A, probably, right? I think if you're looking at this, you're like, oh, A covers this edge, this edge, this edge, this edge, this edge. That seems like a good guess for where to start. And then you see, well, I have G and H. Well, I have to cover both. I have to cover this edge here, so I have to put a guard at least one of these two locations. Right? I need to put a guard on one of these two sides, so let's choose H. Doesn't really matter. Here we have B and C. Again, we need a guard on one of these two locations. So, I don't know, it doesn't really matter. Let's take C, just arbitrarily. And then, let's see, this edge is covered by A, but we're going to need to cover this edge, and we're going to need to cover these two edges. So it seems like maybe E is a good choice. Again, doesn't have to be, but seems like a good choice. So it covers those edges, and this one is covered twice, but that's fine. And we're almost there. The only thing we have left is this one edge. There's no guard that can see down this road, so we can station a guard at F. And like that, every road has now been covered. Right? Every road has now been covered. That gives us a vertex cover of size, was this 5? Alright, maybe you've seen something after doing that example. Maybe something's percolating in the back of the brain there. But let's do one last example, just for practice. If you're starting to feel like something seems familiar, hold on to that. Okay, vertex cover example number 3. So I'm just going to do that weird looking graph we had from before. As a starting point, actually, I guess I spoiled that H connects to everybody. So H is a natural choice. H literally connects to every other vertex. So we're probably going to pick that one. And so it covers all those edges. Now, as you start connecting people, you'll see, let's see, maybe A is a good choice. All right, A is a good choice because it's got a lot of connections. E also has a bunch of connections. Maybe E is a good choice. Put your guard there. Let's see, this is connected. This is covered. This is covered. Okay, F seems like it's mostly there. We do need to get G, I guess, or F. Maybe we'll take G. Put a guard here. Let me see, do we need any more guards? Let's see, we can stare at it and see how many edges are kind of marked. And I think actually at this point there's no more edges which remain unguarded. Of course, feel free to check that. But that gives us a vertex cover. If you believe that, it gives us a vertex cover of size 4. I believe those guys cover all the roads. So now, having seen vertex cover, seen these examples of vertex cover, hopefully the problem makes sense. Do more examples if you need to. What do you notice about them? What do you see that kind of looks familiar? Right. Hopefully what you saw was that the things that are not part of the vertex cover necessarily form an independent set. This is an independent set of size 4. These guys have no edge connecting them. Otherwise, we would need a guard at one of those locations. Therefore, they're an independent set of size 4. Huh. So the vertices not in the vertex cover, it seems like they form an independent set. Weird. You might doubt it because right, these are just some examples. You could try your own. As usual, I encourage you to consider doing that. But yeah, the vertices not in the vertex cover are an independent set. And I kind of hinted at why, right? You shouldn't have an edge connecting any pair in here. Now, this maybe is a good point to mention that for independent sets, is it harder to find, or sorry, for vertex covers, is it harder to find a larger number of elements to be in your vertex cover or a smaller? You know? So is it harder to find vertex cover of size K or K plus 1? Just as a side note. Well, for independent set, it was harder to find larger independent sets or larger cliques, right? The larger the size of the clique, the more restrictions. For a vertex cover, the more vertices you put guards at, the easier it is to find an admissible, a workable solution. So it's harder to find a vertex cover of size K. So there's something complementary happening here. The vertices not in the vertex cover are an independent set, and as you make the vertex cover smaller in size, the independent set becomes bigger. And so it becomes harder to find a small vertex cover and easier if you allow more guards in your vertex cover. Like I could have chosen D to have a guard at its location. It would have been a superfluous choice because I don't need a guard at D, but I could. I could make the vertex cover bigger. All right? So those are some important details. Think about them. Pause the video, stare at it, draw some examples if you need to. Now we're going to do another reduction. Okay. So, for this guy, again, let's imagine that someone out there found a polynomial time algorithm for vertex cover. So let's suppose someone out there, some clever person, found a polynomial time algorithm for vertex cover. Let's show that now independent set is solvable in polynomial time. And here's a good place to try and, again, pause the video and try and do this one maybe on your own. Try and fill in all of this stuff on your own. I've given you some good hints as to how the vertex cover relates to independent set. But otherwise, I'll walk you through it. Okay. So again, I have this picture. It's basically the same picture, but now the vertex cover is the black box operation, the black box code that like our clever friend has figured out how to solve. And we're trying to figure out how to solve independent set using their black box code. So we're going to transform our input in polynomial time. We're going to then put that input into the vertex cover solver, and then whatever it outputs will also be our answer for independent set if we've done this successfully. So again, independent set, I'll just put a subscript IS for vertex cover. I'll put a subscript VC. Let's think about how we change the input to from an independent set to get an equivalent vertex cover problem. Now, so how do we take the inputs to independent set and turn them into a vertex cover input? Well, looking at our previous page, did we change any vertices or edges to get to a problem about independent set? Well, no. Actually, when we found the vertex cover, the independent set was somehow the complementary positions, but we didn't need to change any edges or vertices to see that. So our input for these guys, actually should be the same. No change. That's easy. Where the change actually occurs is in that complementary part. So the size of the vertex cover, an admissible vertex cover, has a relationship to the size of an admissible independent set. In particular, if we want an independent set of size, let's say we want K independent set, we're looking for an independent set of size 4, like in the previous page. So we were looking for an independent set of size 4, and in this case we have 8. I'll actually go with this one. I'll do this one. And let's say we have a total number of vertices of 8. Right, so help if I actually write the right thing, right? Number of vertices is 8. So if you have 8 vertices and you want to find an independent set of size 4, well, then your KVC needs to be everything that's not in that independent set, right? So it needs to be, it doesn't matter which size, these two are the same size. So whichever, it's the size of the independent, size of the number of vertices in the independent set graph or the vertex cover graph minus the number of vertices in your desired independent set. Let me do another one here. So this one's not very interesting because it's 4 and 4. This one's a little bit better. So we want an independent set of size 4, and we found a vertex cover of size 5. That's because we have 9 vertices. So we take 9 minus the 4 we wanted. We needed an independent set. We needed a vertex cover of size 5 to ensure an independent set of size 4. Okay. Hopefully that makes sense. Try it out some on your own examples to see that these two are equivalent problems. If you take an independent set problem, you apply this operation, you've created a vertex cover problem which has the same answers in the independent set problem. Okay. And how long does this take? How long to do this reduction? Well, we're just doing a subtraction operation, and so yeah, we treat those basic operations as constants. So this would be a constant time operation. More importantly, this is a polynomial time algorithm then. So from that reduction, what we see is that independent set is polynomial time reducible to vertex cover, right? And also, using similar logic, we can show that vertex cover is polynomial time reducible to independent set. From these, we know these two problems are equivalent. And then we've also then shown indirectly, I guess, a relationship between clique and vertex cover. Clique is reducible to independent set and polynomial time, which is reducible to vertex cover. Clique. Now, what's interesting here, for these guys, is that even though what we're seeing is pretty obvious, I think for graph problems, like these very similar graph problems, this idea can be extended even further. So for these problems, they also have relationships to other problems which are not directly involving graphs. That's going to make our reductions a little bit trickier to see, right? These reductions hopefully are like the super easy reductions that are obvious once you stare at them. Next time, we're going to think about reductions that are less straightforward, but nonetheless involve hard problems. So the problem we're going to look at is called the satisfiability problem. We'll come back next time, introduce the problem, and introduce a way to reduce it to these other problems we just saw. Okay, thank you.